15th problem. An ideal gas mixture has 30% nitrogen. Molecular weight of nitrogen is 28 and the gamma is 1.4, and the remaining argon molecular weight is 40 kilogram per kilomole and gamma is 1.667. This is by mass. So I can say mass fraction of nitrogen will be equal to 0.3 and that of argon will be equal to 0.7. Okay, it expands in an adiabatic turbine, insulated turbine, from pressure of 600 kilopascals, temperature of 400 degrees centigrade to a pressure of 100 kilopascals and a temperature of 390 Kelvin. Mass flow rate of the mixture is 1 kg per second. M dot equal to 1, that is m dot of the mixture is 1 kg per second. Ambient temperature T naught equal to 298 Kelvin. These are the given data. Determine the rate of change in availability, then irreversibility and the second law of efficiency. 15th problem. So now I got this mass fraction, so I can find the Cp mix. Cp mix is nothing but sigma yi Cpi I equal to 1 to 2 components. So that can be written as first 0.3 into, I can write this is gamma r by r minus 1. So gamma r, this is r divided by r minus gamma minus 1, sorry, gamma r by gamma minus 1. So this is the for nitrogen, plus for argon 0.7 into 1.667 into 8314 divided by the molecular weight, that is gamma r divided by gamma minus 1. So this will be equal to 675.4 joule per kg Kelvin, that is Cp mix. Similarly, R mix I can find. R mix I can find as again 0.3 into 8314 by 28 plus 0.7 into 8314 divided by 40. You can also find this as R U, that is universal gas constant, divided by the molecular weight of the mixture. Molecular weight of the mixture in turn you can get from the mass fractions. Okay, now this will be equal to 234.57 joule per kg Kelvin. Okay, now these are the important properties which we want. Now rate of Exergy change. Rate of Exergy change is here Z minus I1 equal to m dot into H2 minus H1 minus T naught into S2 minus S1. So this is Cp mix, okay, into T2 minus T1 minus T naught into S2 minus S1. We will find that the next step. Continuing, we get mass flow rate is given as 1 kg per second. So this will be 675, that is 675.4 is the Cp into 390 Kelvin final temperature. Initial temperature is 673 Kelvin. Convert into Kelvin minus T naught is 298 into, now I have to apply the S2 minus S1, that is Cp mix into ln of final temperature T2 by T1 minus R. R is 234.57 for the mixture into ln of 100 kilopascals divided by 600 kilopascals. So this will be the expression, correct. So now this will be equal to minus 20657 watts. Okay, so now what this is the final state minus initial state exergy. Now reversible work, the rate at which reversible work is done is the negative of that. So that will be equal to 20657 watts. So this is the reversible work done. Initial state exergy has to be more than the final state exergy to deliver a positive work. So that is what you get this value. Now actual work I want, so apply first law. First law, Q dot for the insulated turbine, so that is 0. Let the work power developed by the turbine is WT dot equal to m dot into H2 minus H1. Kinetic energy and potential energy changes are neglected. So now from this I can find WT equal to 1 into Cp mix 675.4 into initial temperature 673 minus final temperature. Okay, so that will be equal to 191138.2 watts. So this is actual work. You can see that the reversible work is higher than the actual work developed. So I can find the irreversibility as the rate at which reversible rate is W dot reversible minus W dot T, which will be equal to 435 kilowatts. 15,435 kilowatts is lost because of the irreversibility. Second law efficiency, work producing device, the actual power produced divided by the reversible power, which will be equal to 191138.2 divided by 206,573.2, that will be equal to 0.925 or 92.5 percentage. So that is the answer. So you can see that turbine initial exergy is higher and final exergy is lower. So that comes out of the work. When there is no irreversibility, the reversible work comes out to be 206.5 kilowatts. But when you have the actual work calculation, you get it as 191.1 kilowatts. The second law efficiency is about 92.5 percentage. So this is about the problem number 15. 16th problem, a rigid tank 1 meter cube volume initially contains equal volumes of water vapor and liquid water. So let us take a tank. So the volume is 1 meter cube. So initially water and vapor are there. This, so this is 0.5 meter cube and this is also 0.5 meter cube. So now there is a wall located at the top of this. Through a wall located at the top of the tank, this is tank, vapor is taken out. Okay. So that finally the liquid water occupies 0.4 meter cube. So for example like this, liquid, this is 0.4 meter cube. Initially it was 0.5 meter cube. Now vapor occupies the remaining volume. So this is 0.6 meter cube. This is vapor and this is liquid. Always liquid will be at the bottom. So it's a mixture of vapor and liquid always. So this is final state. So this is initial, this is the final state. Heat transfer occurs to the surrounding at 200 degrees. So T naught equal to 200 degrees centigrade. Determine the exergy destroyed. Okay, this is the problem. So we can see that the information given is the total volume of the tank is 1 meter cube. Initially equal volumes of liquid and vapor are present, and after removal of vapor you can see that some evaporation takes place, so that liquid comes down, and finally whatever vapor is above the liquid surface will be accumulated over the liquid surface. So the volume occupied by the vapor will be the total volume minus the volume occupied by the liquid. So this is the condition. So solution: here states, both states are saturated mixture states. And the pressure is given as 1 megapascals. So P is 1 megapascals. So pressure is 1 megapascal. Now let us say go to tables. At 1 megapascal we will take the values required for us. Here 1 megapascal is here. Values of what we want is the saturation, all the values I want. So I will get Vf, that is 1.127 into 10 power minus 3, Vg is 0.194, then Uf is 761.7 and Ug is 2584.84 that we want. Then for the entropy balance I need entropy values. 2.139 is Sf, 6.586 is Sg. So we can retrieve these values. Okay, so we can say Vf equal to 0.001127 meter cube per kg, Vg equal to 0.194 meter cube per kg, Uf equal to 761.7 kilojoule per kg, Ug equal to 2584 kilojoule per kg. Similarly, Sf equal to 2.139 kilojoule per kg Kelvin and Sg equal to 6.586 kilojoule per kg Kelvin. So all the properties we have taken. Now continuing with the solution, initial mass in the tank. Initial mass in the tank is M1 will be equal to, what is that? The volume occupied by the liquid divided by, I will say Vf. That is the specific volume of the liquid at the given pressure of 1 megapascals plus volume occupied by the gas or vapor divided by Vg. So that will be equal to 0.5 divided by 0.001127 plus, again the Vg and Vl are same in the initial condition. So that divided by 0.194, which will be equal to 443.65 kgs plus 2.58 kgs, that will be 446.23 kg. So what is the quality at the state 1? Mass of vapor divided by the mass of water, that will be equal to 2.58. Okay, here divided by the total mass 446.23, that will come out as 0.005578, the quality. So from the quality I can find the enthalpy, which is equal to Uf plus x1 into Ug minus Uf. We have already taken the values of Uf, Ug for 1 megapascals. We substitute them, I get the value of U1 as 772.23 kilojoule per kg. Similarly, I can take S1 value as Sf plus x1 into Sg minus Sf, that will come out as 2.1 65 kilojoule per kg Kelvin. Okay, so that is the state is fixed, and some whatever value we want, we have got this. Similarly, I can do the final mass in the tank. What is that? Final mass is, the volumes are different here now. See, please understand that this when the thing goes out, the pressure drop is actually not very significant. So we can assume that the pressure remains at 1 megapascals. Okay, so here assuming P remains at 1 megapascal, because it's a huge tank and a small amount of vapor is removed, that will not affect the pressure much. So maybe it may drop from 1 megapascal to 0.99 megapascals. So we will assume the pressure to be same. So that means I can use the same properties of Vf, Vg, Uf, Ug, Sf, Sg, etc., which we have retrieved from the saturation pressure tables corresponding to 1 megapascals. Okay, so that assumption can be made. If I make the assumption, I can say M2 will be equal to VL, so this is actually 1 will put, so VL2 divided by Vf plus Vg2 divided by Vg, small vg, that will be equal to 0.4 divided by 0.001127 plus 0.6 divided by 0.194. So that will be equal to 354.92 plus 3.09. So that will be equal to 358.01 kg. Okay. So now what is the quality at the state 2? That will be the mass of vapor, that is 3.09 divided by the total mass, that is 358.01. That comes out as 0.00864. You can see that there is increase in quality because of the vaporization from 0.00578 to 0.00864. So that is about this. Now again, from the values of Us and Ufg, I can calculate U2 as Uf plus x2 into Ug minus Uf, which comes out as 777.44 kilojoule per kg. Similarly, S2 equal to Uf plus x2 times, Sf plus Sg minus Sf into x2, that will be 2.177 kilojoule per kg Kelvin. So now all the properties etc. and required properties state 1, state 2 are retrieved. Now do the calculation. First of all, apply the first law. Please understand that this is a transient problem, because when the valve is open and closed, there is a time duration. Let us say time equals 0 when the valve is open, and when the valve is closed, the time ends. So there is a heat transfer. So, but there is no work transfer. Any other form of work is not there. No displacement work also. So I can say work done is 0. Then I will say d Cv by dt plus m dot E He minus m dot I Hi. So now I can, so this also I can put as basically instead of V I can put U, that is internal energy. That means I am neglecting kinetic energy and potential energy changes. In both control volume, so only internal energy is there. Here also kinetic energy, potential energy for the streams is assumed to be 0. But you can also see that there is no incoming mass, only the vapor goes out. So this is also 0. So this will be the first law. Now I write the mass conservation. dmCv by dt will be equal to m dot I minus m dot E. Now this is 0. So that means I can substitute this here, this, and I will get the q dot equal to, I will write this as d by dt of mCv uCv minus because m dot d equal to minus dmCV by dt. So, I will write m dmCV by dt into He. What is He? H is nothing but Hg, because only vapor goes out. So, Hg at 1 megapascals. So, this is equal to He, because only vapor is going out from the top. So, this is the first law. Integrating, okay, Q, the amount of Q which is transferred is m, to integrate this, so m2 u2 minus m1 u1, the h is constant, so that I will keep it out. So, this if integrate, that will be m2 minus m1 into Hg. What is Hg? Hg at 1 megapascals will be equal to, from the tables, okay, take the value of Hg at 1 megapascal, that is 2778. Okay, so now this is the equation. From this, I know all the values m1, m2 we have calculated, u1, u2 taken from the tables, Hg now we have taken from the table. So, we will say Q equal to 178814.26 kilojoules. So, this is the amount of heat. Okay, very huge amount of heat is lost. Now, entropy balance. Entropy balance. To find the Exergy destroyed, I will say S gen, the rate of entropy generated will be equal to the rate of change of entropy in the control volume, because the transient process, plus the mass flow rate of the outgoing stream into its entropy, minus this, but this is 0, minus q dot by T naught. Okay, now here T naught equal to, as I told, 473 Kelvin. So, now integrate this. Integrating, I get the total entropy generated in the CV equal to, what is that, m to this, if you integrate, this will be, this capital S can be written as small s into m. So, I can integrate this m to s2 minus m1 s1, this is for the CV. So, again m dot t can be substituted as minus dmCV by dt. So, when I integrate that, I will get plus minus, because this is minus dmCV by dt. So, m2 minus m1 into S, Si is incoming entropy. Incoming entropy is nothing but Sg, correct? That is what is incoming entropy, sorry, outgoing entropy, Sc. This Sc is Sg. That is only vapor goes out with its entropy, which is Sg. So, this is this minus q dot, which we have calculated, that q integrated value divided by T naught. So, that will be the total entropy generated. When I substitute the values, I get S gen Cv integrated value as 16.273 kilojoule per Kelvin. Okay, when I integrate with the time, I get kilojoule per Kelvin. What is Exergy destroyed? Exergy destroyed equal to T naught into S gen Cv, which is equal to 473 into 16.273 equal to 7697.13 kilojoules. So, that is about this. So, you can see that the tank is there. What within the tank, there is some liquid, steam storage tank, and liquid is there, and when you take out some vapor, what is the Exergy which is destroyed, which we have found.